Hello everyone, thank you for joining to this webinar. Today we have a webinar dedicated to modeling and analysis of steel bridge orthotropic decks using Midas FEA software. And the purpose of this webinar is to give you recommendations about how to create finite element model of orthotropic deck. Today I will show you the principles of modeling, and I will explain how this model can be used for accurate estimation of ultimate strengths and serviceability of the components and joints. And one of the main and important part of finite element modeling is the moving load applied for estimation of the adverse cases of load position. So in this webinar I will emphasize on this a lot. On this slide you may see the sequence of what will be shown to you. At the beginning I will explain deck components that must be optimized during the bridge design. I explain you the orthotropic deck behavior during the passing of moving load. Then I'll explain you how this behavior affects on the strength and fatigue. I will describe the algorithm, how effectively perform analysis using finite element method approach, how to apply moving load on the deck. I'll explain you how you can use programming skills for developing your own plugins for Midas FEA. This will be explained based on the moving load auto generation for make a working process more effectively. And at the end of webinar, I will give you an example how the described background of this webinar can be used in real practice. So, orthotropic deck is one of the main components of steel bridge structures that require special care on its design and manufacture. Nowadays, if engineer has a deal with such structures, he doesn't have to invent something new, as orthotropic deck components already have some typical and common shapes. This system always includes a deck plate that is defined by longitudinal ribs and transverse crossbeams. And in this deck, crossbeam has T-shape section, longitudinal ribs has closed or open type of sections, and longitudinal ribs are always passed through the crossbeam. So the only that engineer has to do is optimization of deck components, and these components are next is the longitudinal stiffener type and dimensions, is the deck plate thickness and wearing surface thickness, the space of ribs in transverse direction, space of crossbeams in longitudinal direction, the thickness of elements of crossbeam, like a web thickness and width and thickness of bottom flank, then deck to plate and rib to rib connection type. It could be welded or bolted. If it's welded, then there are options how members can be welded. Then optimization of cutouts, the shape of cup holes. Here you have to decide, consider these holes or do not consider them at all. If you need to consider the different shapes available for optimization. And also the engineer has to decide, is it necessary to arrange a bullhead or diaphragm inside the rib at the cross beams? So all these cases can be optimized according to the design calculation, considering both strength and fatigue checks. And of course, finite element method is suitable for this. Yeah, now I'd like to talk about deck behavior. In real practice, the behavior of orthotropic deck components during the passing of moving load along the bridge is quite complex. On this slide, you may see that the structural behavior of the whole deck system can be divided into the next subsystems according to the principle of superposition. The first subsystem is the local deck plate and rib deformation. In this case, during the passing of vehicle, the wheel can be arranged between ribs and above the rib. And based on this, there are different deformed state of plates. Then next subsystem is the overall panel deformation. Due to the concentrated load applied to the deck, it produced a total panel deflection. Next subsystem is a longitudinal local flexure of the rib between cross beams. Generally, this longitudinal rib deformed as a continuous beam, where cross beams have a row of supports, and these supports can be fixed or flexible. Next subsystem is a cross beam flexure and plane. Then cross beam distortion. This distortion of the web of cross beam is because of a local flexure of longitudinal rib between cross beams. And next subsystem is a rib distortion at the cross beam. If concentrated wheel load is arranged between the ribs, a rib has torsion in a place where the intersection of the cross beam, longitudinal rib and a cross beam, if there are cutouts, this torsion produces a local deformation of rib wall and occurrence of secondary stresses. And the final subsystem is a global flexure of main girdle. Here in this case, orthotropic deck is the top flank of the main girdle, and due to bending of the main girdle, longitudinal ribs and deck plate, it carry global axial forces. All right. Now I would like to describe how all this subsystem affects on the strength check and fatigue check. The first subsystem has influence on fatigue life of rib to deck welded connection. In this case, cracks can be initiated at the welds, in the fillet welds in a panel at cross beam, and in the panel and a cross beam. And positional wheel above the rib produce a crack occurrence of number 1, and positional wheel between the ribs has effects on occurring of crack number 2. And during the design, you have to optimize the thickness of deck plate, thickness of wearing surface, and shape of this ribs and space of the ribs in transfer direction. So you have to calculate stresses in rib wall, stresses in the deck plate, and perform fatigue check. Overall panel deformation subsystem. In this case, you have to consider a maximum Midas stress in deck plate to combination of local plate deformation and global bending of the main girdle. This all must be considered for strength check. Also, if you have to consider a connection between a deck plate and a main girdle, and if you have a vertical stiffener of main girdles that connected to the deck plate, you have to provide fatigue check here as well, because it can be occurred here as well. Then rib flexure subsystem. Here this calculation is necessary for optimization of rib shape. You calculate normal and shear stresses in rib due to the local flexure rib and global flexure main girdle. Also, you have to provide joints arrangement in panel, and these connections could be welded or bolted as well. So here that should be provided both a strength check and fatigue check. The next subsystem is cross-beam flexure. Because of existence of cutouts in a cross-beam, the sections are different along this cross-beam. And you have to calculate normal and shear stresses in a section between cutouts, and normal and shear stresses in vertical section of cross-beam. This is all necessary for strength check. Additionally, you need to provide bolted or welded joints in a cross beam. And here you have to provide both a strength check and fatigue check. And the last subsystem is the rib distortion at cross beam. This intersection is the most critical and complex during design optimization. Real practice shows that in this connection, fatigue cracks are mostly initiated in a rib wall at cutouts and in a cross-beam wall where the cutouts as well. But anyway, fine element modeling can solve all these subsystems and help to you in design checks. And Midas FEA software is quite suitable for this. Now, let me explain you a recommended workflow for performance orthotropic deck analysis. According to this recommendation, you may consider 3 steps. First step is the performance of global analysis of the breach. You operate here with a quite simplified model of the whole breach superstructure. For example, you could consider a grillage model, and in this grillage model, longitudinal beams could have section of a main girdle with effective width, and transverse beams they have a section of cross beams with effective width as well. And this model allows you to make most using this model you can optimize a girdle section and plate thickness of this girdle section. You can optimize initial thickness of orthotropic deck plate, and you can define some initial section of longitudinal ribs and shape of these ribs. And this model considers only global flexure subsystem. In the second step, you have a deal with a simplified model of orthotropic deck. In this model, for deck plate, you use shell elements, and inside the shell elements, you arrange beam elements, longitudinal beam elements, and transverse beam elements. Longitudinal beam elements has section of rib, and transverse beam elements has section of cross beam with a centroid offset. This model allows you to make most of the deck components optimization, like cross beam space, rib space, section of cross beam. You can clarify rib type and shape, and you can optimize, and you can perform design of member joints as well. In this model, you apply a dead weight wear surface, and you apply a self-weight of deck plate and moving load cases. Moving load apply as a pressure load based on the wheel contact areas. Pressure load here allows accurately distribute this load from the wheel. In a deck plate, you calculate equivalent Midas stress in shell elements. Then you calculate a beam stresses in ribs and cross beam. And using design code rules, you provide some you provide ultimate strengths and fatigue checks of the components. And the last step, modeling, is working with a detailed fine element model of deck. This model allows you to optimize all other components that can be optimized in the previous 2 steps, like cutout shape, rib bulkheads arrangement. You can clarify the deck thickness, the grain surface thickness. You can also clarify the shape of your longitudinal rib. And this model is like a finalization of the process. Using Midas family software, the optimal link is to use Midas Civil for step number 1 and step number 2, and to use a Midas FEA software for step number 3. So This webinar is focused on detailed modeling, so I will proceed with this in the next slide. Now I would like to go through the finite element modeling process in Midas FEA. And the benefit of Midas FEA is an ability to work simultaneously with the AutoCAD drawings. During the design, you might have some initial drawings of your orthotropic deck components in AutoCAD. So when you start modeling, initially you draw just a cross-beam contour with the rib shapes, with the cutouts, and save it as a DXF file. Then you import this inside the Midas FEA. Then you make surface of cross-beam web. Then you extrude lines making a bottom plane. Then you extrude lines making deck plane and ribs. And all these parts then can be copied, composing the final geometry model of the deck. Once geometry model is done, you are working with a mesh. Here, one important rule: you generate a very fine mesh only in that parts where it's necessary for detailed investigation. Other parts might have relatively coarse mesh size. At zones of interest, the mesh size should be not more than 50 or 20 millimeters. So Midas FEA has mesh size control that allows you manage the mesh quality distribution of the model. Actually, all these modeling principles are described in the introduction to Midas FEA video, so you may find it on YouTube channel and check it later. So after mesh is generated, you apply boundary conditions. For detailed models, boundary conditions can be considered as fixed supports. As for the self-weight, you have to define a self-weight wearing surface. It can be applied as a pressure load on a deck plate. And as for the self-weight of steel members, you can apply a self-weight of, you can define this self-weight as a body force. Now applying moving loads. This is one of the most important parts of orthotropic analysis. And here you need to consider all the necessary load cases that allows you to investigate the adverse members and joints load in the deck. Moving load cases must be considered separately according to the strength check and fatigue check. For the strength check, based on the Eurocode, you may consider two types of load models. It's load model 1 and load model 2. In the orthotropic deck model, you consider a moving load position in panel and as a support in longitudinal direction, and in transverse direction you consider this vehicle position in the middle of crossbeam and at supports. As for the fatigue analysis, Eurocode recommends consider a set of different lorries, and mostly used load model 2, load model C, and load model 4. So the main purpose of fatigue analysis is to get stress ranges at different points of deck members with the pattern of the vehicles along the bridge lane. In this case, you need to consider pattern of lorry along the deck from one panel to the next panel. Additionally, Eurocode gives recommendations on frequency distribution of the wheel in transverse direction. This actually is important because with this you can consider a wheel position above the rib and between ribs for fatigue check. So based on described above, you may notice that during the analysis you have to consider a lot of different positions of vehicle on the deck structure. And in practice, there could be like 50 monoload cases. But anyway, you will see that development of special plugin for Midas FEA can significantly simplify the plan of monoloads. Now I'd like to explain how this plugin can be developed. And it doesn't matter which programming language to use. It's up to you to use your preferable programming language. I'll just show you the idea of workflow, an example of the plugins that I developed for this webinar. So the workflow is next. From detailed model in Midas FEA, you extract a node, coordinates, and element data of deck plate. Midas FEA allows you to extract this data in table format. Then you have to decide what vehicle scheme will be considered in analysis. Each vehicle has its own wheel contact areas and coordinates and positions of these wheels in space. Then you decide what will be a starting position of your vehicle and a final position of your vehicle, and where this vehicle will be arranged in transverse direction. Then, as you know all the deck node coordinates position, and you know coordinates of wheel contact areas, you may find each node that placed inside this wheel contour. And then you may find elements to which these captured nodes are belong, and then you can apply a pressure load on these elements. So all this process can be performed using programming language, and as a result, you will automatically generate a correct vehicle loading of orthotropic deck, like described on the slide. Yeah, now I'd like to show you example of the plugin. This plugin was developed using JavaScript programming language and a Node.js platform. It's like a web-based application. Here, here's a table entry of deck node coordinates. This table format is similar to Midas FEA format, so I just copy from Midas FEA and paste this node coordinates here. This table is for deck elements. The format of the table is the same as in Midas FEA, so I copy from Midas FEA and paste elements data here. Here I define what my monoload analysis case is. It for strength check or for fatigue. Here I define the thickness of wearing surface. It's necessary for correct distribution of wheel load on the deck plate. And here I can decide, consider or do not consider a frequency distribution in transverse direction. And here are the moving load settings. From the drop-down list, I decide which vehicle should be considered. It's a lorry from Eurocode. Here is the scheme of the lorry, and here are the dimensions of wheel contact areas. And below I have to define a starting position of vehicle using the reference wheel, and a final coordinates of final position of vehicle, and number of intermediate steps for the small load case. Okay, now let me show and practice how it works. So this is example of the tail model of orthotropic deck. It's totally approximated using shell elements. So first of all, I activate only deck plate elements. Then I extract node coordinates of this deck plate. So it's from node 1 till node 23 or 23. So I go to mesh, and here's a node table. Here I'm going to find a node table row with a node ID 23023. I copy all these nodes and put it here in this table. Then elements, I have to copy and paste elements. So elements ID from 1 till 22720. So I go to element table, it's here. And copy and paste all these elements inside the table. Yeah, in this example I will consider fatigue case. Lorry number 1. The name is fatigue case, load case. Deck plate original point. It's this point. This point is 0 and 0 for X and Y. And now the starting position of vehicle. So I can decide it here. For example, let's suppose that it will be start from here, and the final position will be somewhere here. So X coordinate will be 5 and 2 meters in the transverse direction. And here's a 14 and 2 meters as well. A number of intermediate steps will be, let's say, 50 iterations. So it's iterative monoid case. So once all this defined, I can generate loads. And here's I generated my pressure loads of different load cases. So this table is similar to a pressure load table in Midas FEA, so I can just copy and paste this table inside the software. In this table, here's the name of load case. You can see like 1, 2, 3. It's based on how many iterations have you defined. Here's the name of load, the pressure, phase pressure load. Here's the element ID, so plugin finds this elements where the will position. And here's the value of the pressure. So I copy all this data. I go to analysis, load, table, and here's the pressure, and pass this data here. And now if I will check my my loads, I can see all these load cases here, and let me go through this loads. Yeah. So you are making like a simulation of moving this load, of moving the slurry along the bridge deck. Now let me show you the results that you can obtain from this analysis. I already have calculated this model. So here are the several options how you can investigate the results. You can display, for example, Midas stress. Here's a Midas stress in a deck plate, and using slider, you can follow stress change in the model during the passing of your vehicle. At the same time, you can check how your structure deformed and how stresses are changed in components. And when you have a deal with the fatigue analysis, it's a very useful feature when you plot the stress time history. For example, you can use extract results. You can select element and extract results from all moving load cases for this element. And build a graph. And from this graph you can find later stress ranges. Alright, so this is briefly described workflow process. So you create a detailed model, then you extract a deck, node coordinates and elements data from Midas FEA and put all this data inside the plugin. You define settings of moving loads, generate the pressure loads, extract them into table of pressure loads and put inside the Midas FEA software. And after that, moving loads will be generated for you. Yeah, now the final part of the webinar. I'd like to show you an example where the described model and background was used in practice. On this slide you may see a single span plate guider bridge with orthotropic deck, and this deck has closed type of longitudinal ribs. The purpose of this analysis is optimization of welded joints rib to rib in panel and welded joints in cross beams. And this bridge supports heavy load traffic, and as for Flexure, for more accurate results and for reflecting a realistic behavior of the structure, we considered 5 different type of lorries and frequency distribution and transfer direction according to the yellow code. And first of all, a simplified orthotropic deck model was considered. In this model, all the lorries were passed and stress fluctuating were investigated. On the slide you may see stress, changing of stresses in the rib at a connection during the passing of different vehicles, and you can see here how stresses are changing as a welded connection across beam. Then Eurocode 3 gives recommendation on stress range and cycles counting. That was done for the stress diagrams at 3 cross-beam connections. Afterwards, what was considered a detailed model with a different wheel action above the rib, between the ribs, and were investigated how stresses are distributed in a rib and a deck plate. And then from yellow code, we're choosing fatigue detailed categories for longitudinal rib joints and for cross beam joints, using fatigue curves and stress ranges from the previous calculation, and using fatigue damage summation based on the polygram minor theory was investigated the fatigue life of each this detail. So here is the table of results, and a calculation shows that these details for longitudinal rib-to-rib connection, these details are suitable for fatigue check, for fatigue life, and these details are not suitable. They are failed as for fatigue check. And as for the crossbeam, all the considered welded type of connections are suitable. Okay, actually this is all that I want to show you in this webinar. I hope it was interesting and helpful for you. If you will have some other questions later, just email to technical support. You will receive a reply. Thank you very much again for joining this webinar, and good luck and goodbye.